Okay. So in the previous lecture, we have been to the Fourier series. Okay, and we have solved the problems based on the Fourier series. We have seen all the types. Okay. Now we have to move forward. Okay. So as we know, there are the several things to deal with the programming. Okay. Most of the times we have two things in computer or IT technology: the software and hardware. Okay. So these things form a complex system, and hence we need to get into the basics, or we need to get into the understand to understand the mathematical model for this. So as we need to understand the mathematical model for the complex system, so we first have to understand what are the basic mathematical components of this complex system. So here we will try to extend our base what we have seen in the first semester. In the first semester, we have seen the complex numbers. Now, these numbers to be extended to complex variables. Okay. So, in this module, we will be extending our ideas of numbers to variables. Okay. So, let's have this. So, the module today we are going to start is complex variables. Okay. So we are familiar with the complex numbers. So what we know is like z is equal to x plus iy being
Excuse me, sir. The screen is not visible.
okay. Yeah, thank you. Okay, so we'll see the complex variables. So let here z is equal to x plus iy be a complex variable. So here we used to consider this as a number. Now we'll consider this as a variable. So be a complex variable with x and y are real variables. Okay. So that's what we have. This x and y are going to be uh, real variables. Okay. These are real variables. Here, this R means reals. Okay. So these are real variables. And we are familiar with this notation I, so which is the square root of -1. Okay, so what we know is we have x is called a real part of z and y is called imaginary part of z. Okay, so now for example, I consider that f of z is equal to z square. So as we write in reals, real function f of x is equal to f of x is equal to x square. So here what I do is I consider the variable x is a real variable in this case. Now we have to extend to the complex variable, so we consider z as a variable. But what we know is we know z is what, x plus iy bracket square. So simplify this. What you will be having, a square plus b square, a plus b bracket square is a square plus 2ab and plus we have b square. Okay. Now simplify, x square plus 2ixy plus I square y square. But what we know about I square, since I square is minus 1. So we can write this as x square minus y square plus 2ixy. Now let us see what we have. We have f of z is equal to x square minus y square minus y square plus I, we have 2xy. So you can see that this function f of z, this I will call as u and this I will call as v. So this function f of z we can write as u plus iv, where u is a function of x and y, and which is x square minus y square. And we have v, again a function of x and y, and which is 2xy. So here what we are able to say that the function of complex variable, this is going to be a function. So the function of complex variable, we have seen that it is again a complex. Okay, so what we can have is, we have this function, the function of complex variable is again complex, is a complex value or a complex function. Okay, so we know that what do we know? The set of natural numbers is a subset of whole numbers. Okay, set of whole numbers is a subset of integers. Okay, this sometimes we write as I or we write as z, which is a subset of the rational numbers. Okay, and then what we know is the set of rational number is a subset of real numbers, and real numbers is a subset of complex. Okay, so anything goes in this category is always a complex number. Okay, so anything goes in this category is always a complex. So basically we can conclude that everything is a complex. Okay, so everything being a complex, only thing that we do not care about imaginary part sometimes. Okay, so basically here we know that everything is going to be complex, and that's why this we need to understand the complex variable and the functions of complex variable. So what we can have is, we can define a complex function. Okay, so let f from c, this c is a complex variable, to c. Okay, this function from c to c, okay, is called a function of complex variable z, which is equal to x plus iy, and is noted as f of z. So that is, we have seen that f of z is equal to u plus iv, where u is the function of x and y, and also b is the function of x and y. And moreover, we call this u. Okay, so and u is real part of complex function f of z. B is imaginary part of complex function f of z. Okay, so this way, starting from the complex variable, we are able to define the complex function. And now, once we have this complex function, as we have to study we have studied the real valued function. So first we define the real numbers, then we define the real valued function. Then we tested the calculus, the different properties of this real valued function, like what happens for the limit. Then after the limit, we have studied continuity. Then after continuity, we have studied differentiability. So after differentiability, we have studied the integration. Okay. So in this semester, we are going to study up to the differentiability and different applications of differentiability of a complex variable. In the next semester, we'll study about the integration. Okay. So now we have to go up to differentiability and we have to explore the different properties of this differentiability. Okay. So once I have defined this function, then next I need to understand how I am able to define the limit in complex. Okay, because limit in real is easy. We know we calculate the left limit and the right limit, and then we see that the left limit and right limit exist and equal, and then we say that is going to be the limiting value of the function when the variable x tends to some position or some value. Okay. Now, the idea of the limit in a real case is similarly applicable in complex variable also or in complex domain also. Okay, so we'll write the definition of the limit of complex function. So we'll consider limit of complex. Okay, these are the basic definitions which has the very much importance. So if we are not able to get this, then we'll be in trouble. So that's why I want you to be attentive and be careful for understanding of this basic concepts. Okay, because these are very important concepts. So here we are going to study the epsilon delta definition of this limit, which is very much equivalent to the left limit and the right limit. Okay, so I'll show you how that exists. Okay, so what we know in the real cases. Okay, so in real cases, what we have limit x tends to a minus f of x. Okay, then this is equal to limit x tends to a plus f of x. And if this thing happens that the left limit is equal to the right limit, then we say the limit exists at x is equal to a f of x, and the limiting value we call it as L. Okay, so this is the real variable case. Okay, so this is what we have in real variables. Now, what we have in complex variable. So this all is written in terms of the epsilon and delta. So how do we write it? Okay, so we can have let f of z. Okay, now we have to be careful that we are in complex domain. So our variable will be a complex variable. Okay, be a function of complex variable complex variable z. Okay, then the function f of z is said to have a limit L at z is equal to z0 if, okay, for every epsilon, okay, greater than 0. Epsilon is a very small number. So for every epsilon greater than 0, there exists a number, there exists a number delta, very small, but greater than 0. There exists a number delta greater than 0 such that whenever the distance between f of z and f of z0 is less than epsilon for all when the distance between z minus z0 is less than delta. So if we have the distance between f of z and L, because L we are considering to have the limit. So whenever the distance between L and f of z is going to be less than delta, whenever the distance between z minus z0 is less than delta. So what it says that, see, what we can have here, suppose we are having this 0 and you have f of z is going to be z. Okay, so we have the curve. Suppose this is the curve. Okay, and we are having z0 here. This is z0. Then this is the value L. So what happens is when we have the distance between z, so this is z0 minus delta and z0 plus delta. So what you will have here, you can see here this distance, this is going to be L plus epsilon and this is going to be L minus epsilon. So the value will be always in the neighborhood of L when you have Z in the neighborhood of Z0. So that is the meaning of this epsilon delta definition. Okay. So what it says that whenever your Z is in the neighborhood of Z0, then the value f of z is in the neighborhood of L, and this is called the delta neighborhood. This is called the epsilon neighborhood. Okay, so whenever we have z in the delta neighborhood of z0, then we have f of z is in the epsilon neighborhood of L. Okay, so that's what we have. Okay, so this we can write in the easy way as, that is, limit of f of z as z tends to z0 is equal to L. Okay. So this definition simply we write as limit z tends to z0 f of z is equal to L. So as we write in case of the real variable. Okay, but this is what the meaning we have for this definition: the epsilon neighborhood and the delta neighborhood. Okay, now we have the continuity. Okay, so this is what we have, the limit. Now, what we know about the continuity? Okay, continuity of complex function. Okay, so as in the real case, okay, so what we know in the real case, so we say the function f of x is continuous. Okay, limit x tends to a, f of x is continuous if its limiting value is same as the function value. Okay, so what we know is this is the limit value and this is going to be the function value. So if limit value is same as the function value, then we say f of x is continuous. So this f is continuous function. Okay, and that's what we have to use in this case of complex variable also. Okay, so what we know about the limit, that it has to satisfy this condition. Now here this L will be replaced. This is the limiting value. This limiting value will be replaced by the value of the function at that particular point. Okay, so we write let f of z be a complex function or a function of complex variable be a function of complex variable z, then f of z is said to be continuous at z is equal to z0 if for every epsilon greater than 0 there exists a delta greater than 0 such that now here we have the distance between f of z minus f at z0. This has to be less than epsilon whenever the distance between z minus z0 is less than delta. And that is what we say. We say limit z tends to z0. As z is tending to z0, this is going to be very small. Then this limit value will tend to f of z0. Okay. So that's how we can say if this is satisfied, then we say the function is going to be continuous. Okay. So as we know, the limit exists. So we know this is going to be the function of complex variable. Once we know this is the function of complex variable, then we test the for limit. So we found that the limit exists at particular time, a particular value z0. Then we test for the continuity, and we got that the function is also continuous at this point z is equal to z0. Okay. Now the question is what happens to differentiability? Okay, so how we are able to define whether the function is going to be differentiable or not? So we have differentiability of function of complex variable, complex function. Okay, so now we have to think of the differentiability of the complex function. So what we can say is, let f of z be a function of complex variable, then f of z is said to be differentiable at z is equal to z0 if. Okay, so again we have to go through the limits. Limit z tends to z0, f of z minus f of z0. As already I am assumed that the function is going to be continuous. So f of z minus f of z0 upon z minus z0 exists. Okay. So if this limit exists, then we say the function is differentiable, and this limit will give the derivative of the function at this particular point. Okay. So this is going to be the derivative of the function at this particular point. Okay. So this way we can define the differentiability. Okay. Now, is there any doubt up to yet that what we have seen? So we are just seen the basic definition. We are just revising what happened in the real case and what is going to happen in the complex variable. So we have to think of what will happen to the complex variable, and these definitions, these basic concepts will help us to understand the calculus of the complex variable or the functions of complex variables. Okay. So is there any doubt up to this for this concepts? Okay, so you got these concepts perfectly. Okay, you don't have any doubt. That's good. Okay, great. Okay, so now once we know that the function is going to be differentiable, then what are the different properties that we need to explore? Okay, so if I know the function is differentiable, then there is a term uh, which we have to study after this. Okay, so once you know the function is differentiable, then we have to consider the analytic function. Okay, okay, analytic function. Okay, so in case of real variable, we always consider the differentiability or the continuity or this in interval. Okay, and now once we see about the complex variable, it is x plus iy, z is equal to x plus iy. So we have this z in both the directions. Okay, so it is in the x direction also, it is in the y direction also, and that's why here either we'll have the region or we'll have a disk. Okay, so the interval in real case. Okay, so we have real case and the correspondence in complex case. So real variable versus complex variable. So we have here interval in real case, and here we have disk D or region R. Okay, so here we always have the interval from A to B. Okay, in real case we always check with the interval A to B. In the complex case we have to check with the disk D or the region R. So please be careful that when we write the interval and when we write the region. Okay. So for a real case, we have the interval. For the complex case, we have the disk or the region. Okay. So here the interval, here the disk. Also, we have to be careful that when I write this R, it is going to be a region, and when we write R, then it is the set of real numbers. So you please have to note this difference. Okay, previously I have written R like this, so it is a set of reals, and now I am writing this R, so it is going to be region. So these are some of the standard notation that we need to understand clearly. Okay, and now onwards, when I write U, so it is going to be the real part of the complex function, and when we write V, it is going to be the imaginary part of the complex function f of z. Okay, now we have to think of analytic function. So how and what is the analytic function? So once we define the derivative, we are able to define the analytic function, which is very important to us. Okay, and in this semester, we'll talk about only analytic function. Okay, and the different properties of analytic function that we are going to explore in this semester. Okay, now when we have the function to be analytic, okay, so the function f of z. Now I do not mention that z is going to be a complex variable. So f of z is a function of complex variable. So the function f of z, which is a function of complex variable. Okay, and this is equal to u plus iv. So u is going to be the real part, v is going to be the imaginary part. So the function f of z is said to be analytic if it is differentiable at every point in a bounded function R or disk. Okay. So as I said, the interval in the real case now becomes the disk or the region. So when I say bounded region, okay, so I can have any bounded region. Okay, this is going to be the bounded region, and then this D. So I can choose the number of disks. Okay, so with any small radius, and fill this region. Okay, so I can have the number of disks in this region. Okay, so any bounded region can be approximated by the open disk. So these are called open disks. Okay, so this is the theorem of the pure mathematics, the complex analysis. Okay, and then we can have this. So that's why any bounded region is very much equivalent to the union of disks. Okay, and hence I said at every point in the bounded region or the disk. Okay, so we don't have to worry about this when we say the bounded region or we say the disk. Okay, so disk is always bounded. Okay, so it is open, but it is bounded. Okay, so we got the function f of z is going to be analytic if it is differentiable at every point in the bounded region or the disk. Now the question is how I am going to test the differentiability of the function at every point. Okay, because as you have seen, so if I draw a disk or if I draw a bounded region, there are infinitely many points. Okay, so if there are infinitely many points, then the question is how we are going to get this. Okay, so think over it and You can give a thought what is possible. I hope you don't have any doubt up to it.
No, sir.
So do you have any doubt up to it? Okay,
No, sir, no doubt.
great. You don't have any doubt. Why not the interval? Correct. So that's good question, Janvi. Okay, so why do you have to take the disk, not the interval? Okay, that's good. Okay, let us see the answer for your question. Okay, so what happens in so the question is, how do we represent a complex number? Okay, so how do we have in real case we have a real line. Okay, so this is a real line starting from 0. We have positive numbers and negative numbers on this side. Now think of the complex region. So the question is, how do you represent a complex? Okay, so if you remember, then we represent the complex like this, x and y. Okay, this is 0. This is imaginary axis. Okay, and this is real axis. Okay, so how I can have one interval only here? Okay, so I cannot have, when I say z, I'll be having x and y. Okay, or this is precisely x plus iy. Okay, so when I have the interval, so this is z minus z0, and here I want this is going to be less than epsilon. Okay, so now see this. Okay, so precisely I want the value less than epsilon. Okay, so what I'll do is, what is z? So what I'll do is, z is equal to, okay, z is equal to x plus iy, and I consider the point z0. So initially we consider the point z0 to be suppose our origin. Okay, and now let us find out what this is going to be. Okay, so what I know is this is going to be x plus iy minus 0 plus i0 less than epsilon. So what this term is, mod of x plus iy less than epsilon. Okay, so what this mod is, so this is square root of x square plus y square less than epsilon. Squaring on both sides, what will have? This will be x square plus y square less than epsilon square. So if you remember what this equation is, x square plus y square is equal to a square. Can you give me what this equation represents numerically?
Circle.
Yeah, Janvi.
So,
Yeah, what this equation represents geometrically?
circle.
Circle, correct? So what it means, this is going to be a circle. Okay, and now draw a circle here. So suppose I have this point. Okay, so the origin I have considered to be z0, and I have considered epsilon to be so this is going to be epsilon. So what I have to do is I have to consider the area, okay, which is inside this circle. Okay, because what we have this x square plus y square is less than epsilon square. Okay, what we have, x square plus y square is less than epsilon square, and that's why what you will get, you will get the area inside the circle. So circle is a boundary, and what we get is area inside the circle. You cut this boundary, and what you will get? Then we what will get?
A disk.
disk. So that's why we have disk in complex. So I hope I have explained your query.
Yes, sir. Got it, sir.
Yeah, good. Okay, so this is how we get the disk in complex, and that's why I'm directly using that to be disk. Good question. Okay, so now the question is what or how we are able to test whether this function is analytic at every point or it is differentiable at every point or not. Okay, so there are infinitely many points in the disk. Okay, there are infinitely many points in the region. So it will become difficult to test whether the function is differentiable at every point or not. And now, if I want to know whether my function is analytic or not, then I have to consider some criteria, okay, which will be necessary and sufficient to understand whether the function is going to be analytic or not. So we need to understand what is the criteria. Okay, so we have necessary and sufficient conditions for function to be analytic. Okay, so what are the necessary and sufficient conditions for analytic function? Okay, so that we need to understand. Okay, so what are these conditions we have? Okay, so we'll try to think of it. Okay, so let f of z is equal to u plus iv be and be a function of complex variable z. Then the necessary and sufficient conditions for f of z to be analytic. Ah, okay, so what are the conditions? The first condition is that w by wx. I hope we have studied partial derivatives in sem 1. So that we are going to use here. W by wx is equal to w by wy and w by wy is equal to minus w by wx. Also, we have studied the exact differential equation. So these are the conditions. Okay. So these equations are called Cauchy. Okay. So please be careful. Cauchy. Some people call this as Cauchy. Okay. So Cauchy Riemann equations. So in abbreviation, you can have the abbreviation CR equations. Okay, so these are called CR equations or Cauchy-Riemann equations. So W by Wx is equal to W by Wy, and W by Wy is equal to minus W by Wx. Okay, so these are the Cauchy-Riemann equations. These are necessary but not sufficient. Okay, and that's why we need to know the necessary and sufficient conditions. So this condition is necessary but not sufficient. So we have one more condition. So what is that condition? And we have the second condition, okay, which is very important. Okay, and the second condition is that w by x, w by y, w by x, and w by y. That means all the first order partial derivatives that I have calculated here, okay, are continuous in x and y. Okay, so that's why the continuity that we have seen is very much important. And if you can see, this u is a real function, v is a real function. So these functions has to be tested in real domain for the continuity. Okay, the next important thing that we need to understand is what we can have. Okay, so what we'll have if these functions are not continuous, or which functions are continuous. So can you give me what is the continuous function you are known up to 8? What functions are continuous functions? So which are the continuous function? So what do you know about the continuous function? Which continuous functions you know? Sin x, that's good. Again, so only function you know that sin is continuous. X is equal to 1. Okay, that's good. So basically, one thing we need to understand: all the trigonometric functions are continuous. Okay. The most important thing that we have seen a rule. Okay, u into v for integration by parts rule, and there we have decided the hierarchy of the functions, the order of the functions. What will be u and what will be v? So that all functions are going to be continuous. Okay. So what are the continuous function? Logarithmic function is a continuous function. Inverse trigonometric is a continuous function. Algebraic or polynomial function is a continuous function. So even though constant is a polynomial of degree 0, so it is continuous. Then we have trigonometric function, which is a continuous function. And also we have an exponential function, which is a continuous function. Okay. So these all functions are going to be continuous. Now the question is, which function is not continuous? Okay, so if I say that these functions are going to be continuous, then which is not continuous, that is equally important. Okay, so here you are supposed to identify function directly without testing. You are not supposed to test the continuity, but you are able to identify the function directly, whether it is continuous or whether it is not continuous. Okay, so the most important thing that the function which is not continuous is a point function. Okay, so suppose you have only one point, then we cannot test the continuity of that point, and hence rest of the functions are going to be continuous. But if there is only point function, then it is not going to be continuous. Okay, and that's what we have to think. Okay, so